the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics podcast. I'm your host, Parker.
And I am Ray, and we welcome you to episode 34, where today, very, very, very exciting,
New
because
series
we announced
alert.
this, I think, 10 or 11 episodes ago. History of Physics.
History of Physics. We are starting a new series. We talked about this a little bit in a previous episode, and so what we're going to do is each of us has picked a physicist or mathematician from the past that has influenced the field very, very heavily, right? And so obviously the two names are already in the title. We're gonna make it all nice. We're gonna say History of Physics dash, and then the two names that we picked.
The two names. I mean, do we really have to keep it a surprise, though? I think, they've already seen the name.
Yeah, I mean, I'm just explaining it though. Still.
Okay.
So today I picked Isaac Newton because he is just the founding father of classical mechanics and calculus, and we're going to get into that 100%.
That's true.
Who did you pick?
And today I picked Richard Feynman, who, not the founding fathers, but one of the very important people relating to quantum mechanics. And one of my inspirations, actually, when I was a kid. So, yeah.
So we just want to apologize as well. We were supposed to post on Saturday, but on Friday we actually had a 24-hour calculus exam, and so we postponed the recording to the day after, and then we're going to post this on Monday. So this is coming out on Monday, 10 a.m. So yeah, I mean, unless we have another midterm, we're probably not going to do this again. We're going to post next Saturday as well.
Every Saturday.
Yeah. We have a fire interview coming up this Saturday. We already have it planned out. It's going to be awesome. If you guys are into the YouTube math community, you guys are going to love this interview.
I think it's pretty cool, for sure.
Yeah. Stay tuned, everybody. Also, quick update. Quick update. 1,300 followers. Let's go. We're probably going to hit 1,500 in the next 2 weeks. So that's going to be great.
Okay. Relax with that. 2 weeks?
Yeah, I mean, we get about 100 per week, so.
Oh, okay.
Yeah.
Okay, that's fair.
Yeah, that's been the trend so far.
That's something cool.
Yeah, that's going to be awesome. So
that's going to be crazy.
All right, let's get into it. Do you want to start or should I start?
You can go for it. Classical mechanics comes first, I guess.
All right, let's start this. So Isaac Newton. Also, quick disclaimer, okay? Obviously, most of our information is coming from Wikipedia because that is the greatest resource of all time. But we're going to try as hard as we can to not just read off of the website. We're going to present the information and then talk about it, give our own personal experiences, opinions.
To be honest, though, like a lot of my Richard Feynman stuff, I couldn't really get from Wikipedia because you know how Wikipedia, especially when it's a little scientific, how it goes crazy scientific,
that's true.
Like pretty hard. So I literally couldn't really understand Wikipedia. So not Wikipedia for me, but I did use other sources for sure. So
all right.
Disclaimer. Yeah.
So let's get into it. If you didn't know, back in the 17th century, the calendar was a bit different. And so the dates that I'm going to be presenting are the old style dates and not the new style dates. So they're the dates before they changed the calendar.
Wasn't it like Julian and old Julian?
Something like that.
Yes,
but
I don't know.
Isaac Newton was actually born on Christmas Day.
What?
1642. Take that in, all right? Quick little side note, by the way. I'm pretty sure this might, I know this is true for some pair of people, right? So the day that Albert Einstein died was the same day of the year that Stephen Hawking was born.
No. Other way around. Albert Einstein was born on Pi Day. Stephen Hawking died on Pi Day.
Okay,
which
yeah,
is 14th of March.
There you go.
Yeah.
So that's That's a little anecdote right there.
Yeah,
okay.
I think that's actually pretty cool. I think that's really,
Yeah,
really cool.
that is
Big
cool.
coincidence.
I mean, it's not cool, but you know.
I mean, okay, sorry. Not cool, but it's an interesting coincidence.
Yeah.
I think.
Also,
Yeah.
another anecdote is on Pi Day, when the day that Stephen Hawking died, I was actually at the observatory in London. I forget what it's
Oh,
called.
what?
I forget what it's called. What's the? Oh yeah, wait, is the Greenwich, right? Isn't it? Wait, let
Isn't
me
it
Google this.
Greenwich? No, wait. I'm thinking about something else.
Anyways, okay. I'm not gonna search this up, but
Yeah,
there's an
we're not sure.
observatory.
Again, the big disclaimer.
Yeah, there's an observatory in London, with like these cool like old telescopes and all these things, and it's on the meridian. So yeah, I'm pretty sure it's called the Greenwich, something like that. But yeah, I was there the day that
That's cool.
Stephen Hawking died. Okay, moving on.
Moving on. To
25th
Isaac Newton.
of December, 1642. He was born. Okay, one thing I just want to note is that you got to put yourself in the mindset of a person living at that time. Okay, you're going to class. You go to quote unquote physics class, but you're not learning like F equals ma, because that has yet to
Because the
appear.
guy
Okay?
who made it doesn't even exist yet.
Nowadays the first thing you learn in a physics class is F equals ma, but back then
yeah,
try to think.
Yes.
Try to think. Most of the things you're doing is just like like Aristotelian like philosophy / like just natural observations. Okay, so there's a lot of like analytics stuff that just didn't exist back then.
Mm-hmm.
So Newton's early life, all right, he was you know, living in London at the time, and he didn't, I don't think he left London at any point. But anyways,
No idea.
he was
no
enrolled.
idea whatsoever.
I'm not asking you. I'm just
Yeah,
saying.
okay.
Yep. So yeah, he was enrolled in a school called King's School, right? And this was in Grantham. This is just a town, right? And he actually was pulled out of school at the age of 12. His mom took him out. His mom's like, "All right, you're gonna become a farmer," because I guess that's what people did back then. They didn't really value school as much as it is valued today. Mm-hmm. Which makes sense, but you know, Newton hated farming. He thought it was absolutely horrendous. So, his uncle, who's actually a graduate of the University of Cambridge, he saw that Newton was a bright mind. He was like, man, he's got a lot of potential. So he convinced his mom. He's like, yo, okay, we gotta send him back to school. He's gonna achieve some great things. So his mom was persuaded. His mom just let him go back to school, and so he went back
and that uncle.
Yeah,
that uncle saved our lives.
Literally,
that uncle made everything possible.
If you think about it, literally. So yeah, he went back to school, and he graduated. Like, I don't know if it's called primary school or whatever, secondary school. He graduated the school that you went to in the 1600s, and then he got into Cambridge University. So by the time he got to Cambridge, he had to work as a valet, right, to pay off his studies. But very, very soon into his stay at Cambridge, he was awarded with a 4-year what's it called, scholarship.
Oh, there
so
we go.
Everything was paid for. So once he actually graduated, wait, there's one thing I forgot to piece together. It was when the plague happened.
Oh.
Because his school actually closed during the plague, and so that's when he went home. You know, obviously he can't do anything during the plague. Kind of like our situation right now, right? He was in a pandemic. He had to stay home and just
nice relation to modern times.
Exactly. So he went home, and that's when he actually had his biggest enlightenments to, up to his what's the word I'm looking for? His biggest achievements. Yeah, right.
Yeah.
So this was during the plague of 1665. That's when the school closed. Now notice I said 1665. Newton was 23 years old, okay? So just keep that in mind. He was 23 years old. During the next 2 years, okay, that he was at home, just bored, working on his self-studies and all that, he essentially invented calculus. He made great advancements in the field of optics, and he came up with the law of gravitation, the law of universal gravitation. Mind
this guy's
you,
23.
Mind you, he was just chilling at home, just writing things down, and he came up with all these crazy advancements. Imagine us during the summer. We just invent like some new field of math, and then we come back to school the next year, and we're like, oh yeah, by the way,
here you go, you're welcome. That's your syllabus.
This is how you connect quantum mechanics and general relativity.
Yo, this guy was very, very, very cool for sure. Especially in his time, Newton was like regarded as a god, right? Like there were so many debates with like Newton and other people of his time. Mm-hmm. Where he would simply win the debate over no scientific reason given, but right. Simply because he was the more popular scientist.
And that's actually a problem of the past.
Yeah, it definitely was, definitely.
Like the scientific clout was definitely an issue. If you were like well known back in the day, you could essentially just be like, no, I'm right. And then, end of discussion.
So and I swear we read some kind of debate like this, right?
Sorry?
Or we know of some kind of debate where Newton basically simply said no. And even though the opposing the opposing party had perfectly good scientific evidence of their fact, Newton simply said no, and the rest of the world believed him because he was the more popular scientist.
It's the debate of particle versus wave for light.
Oh, yes.
I'm pretty sure that's it.
Oh, yeah, that was it, right?
Newton, I don't remember what he thought, actually.
Newton stuck with particle, right?
I don't remember. This was a year ago. We saw this in class.
We're not exactly sure. But I'm pretty sure Newton stuck with particle, and I don't even remember the opposing person, to be honest, but the other person was going with wave and had crazy scientific evidence to back the fact that light was a wave because it exhibited wave-like properties, but Newton simply said no, that's wrong, and okay, so it just wasn't addressed.
Okay, yeah, so I just searched this up. So Newton did think that light could only be explained if it was made of particles.
Okay.
And taken how little like open-mindedness this reflected of his character, right? Because you had Huygens, who was performing the double slit experiment, and he's like, this makes no sense, right? Like I'm sending light, and it's not producing just two slits of light on the board. It's producing this interference pattern. Mm-hmm. This is very good evidence, right?
Yeah.
Very compelling evidence that light is in fact a wave. But Newton just said, you know what? I don't think that fits with my ideology. And so
that's it.
Yeah.
Game over.
That's my opinion on that.
Yep.
So you can actually this is just going back to the topic of things that Newton did. You can actually go on YouTube, and I think this is a video with a number file. He went to like an archive and looked at original documents of like Newton's journals of when he was stuck at home, and he was just writing things, and the notation he was using.
They show this on YouTube?
Yeah, they showed it on YouTube. It's very interesting.
That's insane.
Yeah, and so they had like the documentation of him
Yeah.
describing like infinitely small increments, and of course he wasn't using Leibniz notation because if you don't know this, they were pretty much rivals.
He was
And
using the F prime notation, right?
right, he was using the
Yeah.
prime notation, while Leibniz was using the d by dx notation. And so he was using q and p, like lowercase q and lowercase p, to denote basically dy and dx. And so he went through the equations, right? He was deriving equations for the derivatives of functions by substituting x for x plus q and y for y plus p. And then, he came to the conclusion that, he was solving derivatives. It took a lot of algebra to go through, right? He didn't have the power rule and the chain rule and all that. So what he was doing is he was discovering derivatives one at a time. Like, think about that for 1 second.
That's pretty.
Imagine you're
crazy.
sitting at your desk and you're like, okay, I see that x squared becomes 2x, and I see that x to the third power becomes 3x squared. And he was trying to piece together this puzzle of writing derivatives eloquently. And same thing goes for integration as well, which is, people think that integration was made before.
Yeah, I was actually just gonna say that. Like, I'm pretty sure like he started with integration, right?
Yeah, I mean, there's a lot of.
I think. I'm not sure, but I think I heard that somewhere.
Not that much. There's not much we can say for certain, because this was, almost 400 years ago. So information gets lost and people hear things and stick to it. So the truth kind of gets bent in that way. But nonetheless, he invented calculus. So
it's also kind of like the apple falling on his head thing,
Yeah.
Like, no one really knows if that's true. A lot of people say that he saw an apple fall. Some people say an apple fell on his head. Some people say that was never even the case. He just came up with a law for it. So, because it was so long ago, like, there's just not enough concrete evidence for what exactly happened. So
yeah, so
we're not exactly
unfortunately, I will burst the bubble here.
Oh,
A lot of people think that Newton was sitting under a tree, an apple fell on his head, and he just, the equation for gravitation just popped into his head. He's like, oh my god, GMM over R squared. That's
impossible.
Unfortunately, that is not how that happened. But the reality is that a lot of mathematical and experimental work went into discovering that law, and it's not a result of just watching an apple fall off a tree. Unfortunately,
yeah,
that would be an amazing story if it actually was true. So yeah, we're coming up at around halfway through the podcast, but I can say one more thing on Isaac Newton.
Okay.
Classical mechanics. I did mention this in the beginning of the podcast, that F equals ma. That is the second law, right? Newton's second law.
Yeah.
First law is inertia, and the third law is every action has equal and opposite reaction. If you can understand those three laws fundamentally, you will pretty much I'm not saying you'll be good at physics if you just understand those laws, but like I'd say
you'll have a good understanding.
Yeah, like 80% of physics is just kind of wrapping your head around what is actually happening in this physical world. And so if you think about what forces actually are, like when you push on a wall and you feel the wall pushing back on you, think about what's happening there. Think about how the wall isn't accelerating. And these are just casual little experiments you can do, I guess. But yeah, I always think about when I walk, when I'm walking. I don't. Okay, that's kind of a lie. I don't always think about
You
this.
don't always think about that. I was just gonna say, there's no way.
Sometimes I think about this. I'll be walking, and I'm thinking my foot is applying the same amount of force pushing backwards that the earth is pushing on my body, and that's what's causing me to move forward. But anyways, that is just a little. I don't know why.
You think about that every
I don't
time
know. I don't know why I would think about that. It's just
such a random thing, man.
I mean, it's Newton's third law. Every
It's a pretty important law for sure.
Every action, like when you jump off of the earth, you're actually moving the center of mass higher up, to where you are, between you and the earth.
Yeah.
And you're actually pushing the earth away from you. You're not just moving away from the earth. The earth is moving away from you at the same not the same rate. What am I trying to say?
Well, technically with the same force that you push down on it,
with the same force
that you're going up, you push down on it.
Oh, so technically the same momentum, right?
Yeah, you can kind of say it like the same impulse, like the change.
Yeah,
for sure. Okay, so now getting into Richard Feynman. So Richard Feynman, again, I think I already said this, but Richard Feynman was actually kind of childhood inspiration, mainly because on YouTube there are many Richard Feynman videos, and obviously as a kid I wouldn't really watch the physics ones, but I used to watch a lot of his videos where he just explains just concepts. And there's this one video on YouTube that I basically recommend everyone should watch to really appreciate the character of Richard Feynman. The video is literally called Richard Feynman Why, where he basically explains why it is so hard to answer a question that begins with the word why. Why does this happen? Well, there's so many ways to answer. Anyways, he explains it in such a good way. I can't really do it justice, but it's definitely worth watching. So Richard Feynman, why? You really get to know his character. And he's a funny guy. He's a cool guy. But another big reason for why I really love him is his teaching skills. If you watch like a Richard Feynman video of any of his lectures, you'll see the way he teaches is so phenomenal and so simplistic without getting too difficult that it's kind of like unparalleled with any other teaching experience. I just think Richard Feynman is a really cool guy, basically.
And he has a lot of lectures up on YouTube.
Yeah, he does on YouTube.
Which is kind of surprising considering, like, when was he born?
1918.
Yeah.
Died 1988. So obviously YouTube wasn't around, but there was video.
Yeah, but that's kind of surprising that his lectures were like caught on film.
Yeah, I know, right? Like that's very impressive.
Yeah.
I mean, that back in the like probably what, maybe 1960s where he was being recorded, yeah.
Yeah.
And like, I mean, not that the quality is like 1080p, but it's not terrible, you know?
Yeah.
Okay, so
come to think of it.
Yeah.
Wait, when did Albert Einstein die? He died after the war.
He died like 1930. He got a Nobel Prize. He died like 35 or something, right?
No, he was alive during the war. So he died after the war.
Oh yeah. Wait,
like
yeah, that's true.
Past 1945. But anyways, if you think about it, if you do the math in your head real quick, Richard Feynman was already like 20, 30 years old by the time that Einstein died. Like, imagine being in that position right now. Like, that
he was actually mentored by Albert Einstein. He sat in a lot of his classes. Yeah. So they actually so basically, I mean, as I was gonna get to in a little bit of his history, he was a very, very smart guy as a kid. Like, very smart, to the point where he was like winning the world math competitions and impressing so many people around the world, to the point where even Albert Einstein met him, basically.
Damn.
Yeah, so anyway, that's really cool. So Albert Einstein, quick fact check, born 1979, died 1955. So yeah, just after a little after the war. Yeah.
Mm-hmm.
So yeah, I think that's pretty cool that Feynman and Einstein were also kind of, you know, with each other, talking to each other a lot and stuff like that. Because a lot of their, I mean, I'm not sure about which ones, obviously, but a lot of Feynman's, you know, principles in quantum mechanics is kind of something that Albert Einstein rejected, right? Because Albert did not, or Einstein did not even believe in the idea of quantum mechanics. So it was kind of like a fun thing there. But anyways, so a little bit of backstory before we get into what Feynman did to really change the scientific world. So he had a younger sister, and I think this is a pretty cool story. He had a younger sister, I think 8 or 9 years younger than him, and his mother did not believe that the sister could achieve anything. So she basically only endorsed Richard Feynman, and only said, "Oh, you can do great things. You can do great things."
It's kind of sad.
But now here's where the awesome part comes in. Richard was so nice to his younger sister that he actually helped her study, go through school, go through college, to the point where in her later stages she became an astrophysicist.
Oh.
So I think that's crazy. Mother was like, you're not achieving anything, astrophysicist.
Yeah.
I think that's pretty cool.
That's a nice story.
Yeah, that's definitely really impressive. And very similar to Newton, before he, like when I say very similar, I mean like just very smart at a very young age. Before he went to college, he thought of the idea of the half derivative, or like fractional calculus, where you know how we can take the second and third derivative. What if we can take the half derivative of a function? And
Isn't
turns
that
out
some
there
type
is
of
an
integral?
operator like that. Yeah. So he was just imagining, and basically he made up his own set and his own theory for how to solve fractional calculus. And I think that was very impressive. This was before college. This is before
He was in high
college.
school?
Like that's crazy.
That is insane. I don't even listen. I've watched I think a couple of videos on fractional calculus, and I've retained nothing. Like I don't know what a half derivative even represents.
I know it's definitely a hard concept to get around.
What about complex?
I'm not too sure either.
What about complex derivatives?
Okay. We're not getting there. We're not getting there. That's a little too complicated for now.
Yeah.
So other things that he achieved was I think again I did mention this. He aced many math competitions around the world, the Putnam exam, the New York University math competition, for which he was recognized, by people and by colleges, by universities, to the point where he got into MIT for his undergraduate. But also very kind of sad story here. He originally applied to Columbia, where he was rejected because they already had the total number of Jewish people that they wanted for the year. Yeah, so they didn't take him in.
He
went to MIT. They lost Richard Feynman because of this. I mean, obviously times were different back then.
No way.
But that's crazy. So in college, he actually kind of shifted a lot. He started with a math major, and then he went on to electrical engineering, all the way to the other side. And then he said, I want to find some common middle ground. So he chose physics. So this was kind of quote unquote, he wanted like somewhere in between. So he chose physics, I guess. And after graduating from MIT, he got his PhD at Princeton, where he wrote his doctoral thesis, The Principle of Least Action in Quantum Mechanics.
What about masters?
I think he just did at Princeton. I'm not sure if he did like separate things.
All right.
Do you have to do separate master or PhD? Because I know that some people kind of do it in one. No,
I don't think it's necessary.
Yeah, so I think no, because all the information I could find about him was he did his undergraduate here, and then he graduated from Princeton with a PhD. That's it.
Okay.
So I'm just assuming he did his PhD at Princeton, right? So this paper, The Principle of Least Action in Quantum Mechanics, is kind of what put Richard Feynman on the map. It's what got professors around the world looking at this thesis and just being like, whoa, this is crazy. because what he formulated, I'm not going to talk too much about it because I'm going to go into it when I'm talking about like the science part of it. But he formulated something known as the path integral formulation of quantum mechanics. Now, don't get too confused. I'm going to explain everything just in a bit. And he also showed something very important that today we call Feynman diagrams. Also very important, once again, in quantum mechanics. A little more interesting aside was that while he was studying in Princeton, even without his graduate degree, he was recruited for the Manhattan Project, where he was actually helping quite a lot on, making, I think he was responsible for making a uranium hydride bomb, but then that was too expensive or something like that. So he was doing a lot of work in that too. So yeah, I mean, all in all, he was a pretty busy guy, I think. He did a lot of things for sure. Very, very, very smart guy. But now for the fun part, the scientific contributions. What did he contribute to modern science? Well, he contributed a lot. So the first thing, as I said, right, path integral. So the path integral, easiest way to say this. Let's say there's a point A in space. There's a point B in space. What is the probability that a particle in point A will move to point B after some amount of time? Now, classically speaking, right, just with Newton's laws of mechanics, you can just use the velocity of the particle, the forces on the particle, and you can tell it's going to take this much time. But with quantum mechanics, there's not just one path that this particle can take. And I think we've said this many times, right? Superposition, multiple states, but because of that, it can be in multiple places at the same time. And because of that, it can take infinitely many paths from point A to point B. So what Feynman came up with was a way to summarize all the paths taken from point A to point B to get one consistent answer. Whether the probability of the particle from point A moving to point B in some time. So this process was obviously not known to many people because they didn't, you know that you can just sum up all the probabilities. And what he did and how he did it was very simply, of course, but very complicated to us, but very simply for him, and completely revolutionized what we call science, because the path integral is a very important mathematical tool. And I'm not saying I don't think he came up with the integral itself, but he definitely came up with the idea of how to, sum up all the paths and then kind of take that integral. And that was his idea. And I think that's really, really interesting. Again, very, very applicable in quantum mechanics. Mm-hmm. Another cool thing was Feynman diagrams.
Do we learn path integrals in math first or in physics?
That is a fantastic question.
TBD.
I mean, it would make sense to learn it in math, though. Even though it is highly applicable in physics. Because, I think,
all you really need to know is integration, and then if you just have to apply it in a certain way.
Yeah.
You'd learn that in physics.
That's the basic idea. But, I can definitely kind of already see a proof in my head forming,
God.
Something like, for all paths, the path integral is defined by this or something like that. So, I think, to be honest, we might see it in math. I'm not actually sure, but it would be really cool to definitely see a path integral, because I don't think Parker and I know exactly what that is as of this moment.
Nope.
No, sir. Okay, so Feynman diagrams are another very important part of quantum mechanics. Again, as I said, Feynman is basically a quantum god. He is just mainly focused in quantum mechanics, quantum electrodynamics, quantum chromodynamics. All quantum is basically his field. So Feynman diagrams is a simple way to represent interactions of particles. Simply two particles interacting with each other, like two electrons. If two electrons are near each other, what happens? So they actually exchange a certain particle. What particle is that? How do you show it? Feynman diagrams. Feynman diagrams are a very, very basic tool to represent quantum behavior. That's basically, I think, a very pretty simple way to put it. It's a way to represent how subatomic particles move and how they interact with each other. And obviously over time. It's mainly all over time.
Mm-hmm.
another very, very awesome thing. He's done so many awesome things. For which he won his Nobel Prize for was quantum electrodynamics, which is kind of like the interaction between light and matter. Now, I don't want to go too deep into QED itself because I think it's a very complicated subject and requires a whole new video itself.
And also,
if you but he basically won the Nobel Prize for that. Yeah, sorry. Continue.
Yeah, if you want to learn more about quantum electrodynamics, he actually wrote a book called QED, The Strange Theory of Light and Matter. Mm-hmm. So yeah, you can. This was actually recommended to us by our quantum mechanics professor. Right?
Yeah.
Yeah.
Did he not also recommend the Feynman lectures, which is also a book, I believe?
Yeah, no, the Feynman lectures are basically like textbooks.
Yeah, it's basically like a textbook, right, of all the stuff that he does.
Yeah.
And that's just insane. That's just insane.
Yeah, and you can actually buy those. They're $300 at Chapters.
Oh my!
I saw it once.
Oh my!
Yeah.
$300?
Yeah.
Wait.
And there's 3 books. Wow. There's 3 volumes.
Oh, so all 3 volumes for $300.
Yeah, that's right.
I mean, that's not too bad for a textbook, actually.
Yeah,
that's not too bad.
You can probably find them like used or something cheaper.
What if you can just find like an online version? Download PDF.
You can.
PDF and link.
No,
link down below.
It's actually public domain. You can find them online. Like there's a website with all the lectures on physics.
Oh wow, So that's definitely recommended for anyone who's interested in seeing this guy and knowing more about him. But again, like definitely recommended to. I mean, I think most people know Isaac Newton. I don't think that has to be really reiterated. But a lot of people really don't know who Richard Feynman is. And I think for those of you who are slightly or a little interested in, physics or particle physics, will definitely enjoy him so much. Very, very, very cool guy.
Sure. And just to drop the link, it's just feynmanlectures.caltech.edu, and all the volumes are up there. And they also include like photos.
But you got to buy it from there, eh?
No. Like it's like published online.
Oh, just download PDF?
Not even. It's like you click on the volume, you click on the chapter, and it's
like it's all in front of you.
Yeah, it's all there.
Oh, that's very interesting. That's cool.
Yeah,
that is cool.
So you can, if you want to learn more, like Feynman has literally done lectures on everything, from probabilities to space-time to quantum mechanics to insane, everything. You can go online, go to his lectures. They're not like lectures; they're called lectures, but it's just like his textbooks, his writings, and you can just learn about basically anything.
Basically any part of quantum mechanics.
Not even quantum mechanics, just physics. Like
he basically also talks a lot about just physics in general. Yeah, that's actually true. Even though he did most of his work in quantum mechanics, he's just, as I said, just a fantastic teacher in general. Like again, if you watch his videos, just phenomenal. Like he just, the charisma that he has when he comes on and when he's talking, like. You don't see that in many teachers now, or any teachers nowadays. Like that is
that's
like
not entirely true.
Okay. Sorry. Not any, but you don't see that in many teachers nowadays. Like you see that in a few teachers. Like that, that excitement, that charisma when he comes on, and I don't know, it's just very enjoyable to even watch. So.
All right. So that kind of concludes our first episode on the history of physics.
Ooh, let us know if you liked it, and let us know also if you want us to do any specific people, because we have some people in mind for the next few episodes. But if you guys have any recommendations, put it in YouTube comments, email, Instagram. Parker will tell you.
That's right. So email uft.math.physics@gmail.com. Instagram is math.physics.podcast. Make sure to leave a comment on YouTube or send us an email, or you can also leave a review anywhere you're listening to this. Make sure to follow on Spotify. Anywhere else you would like. I'm going to drop the link to the Feynman lectures in the description of this podcast.
I'm actually also going to drop the Richard Feynman why video. I'm telling you, that's so worth it.
Yeah, we'll definitely link it. Yeah. So, We'll see you on Saturday with a fire interview. So yeah, this has been episode number 34 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
All right, peace.